Classmates, when you see ginkgo leaf extract tablets in a pharmacy, have you ever wondered how these active ingredients are extracted from plants? Today, we will explore the extraction, separation, and identification techniques of flavonoids to see how these natural active ingredients can stand out from plants. First, extraction techniques of flavonoids. The extraction of flavonoids mainly involves selecting appropriate methods based on their solubility. Commonly used methods include solvent extraction and alkaline dissolution, followed by acid precipitation. Solvent extraction is the most commonly used method. Its principle is like dissolves like, depending on their solubility properties. Both free flavonoid glycan and flavonoid glycosides can be extracted using methanol or ethanol. Due to the strong lipophilic of flavonoid glycan, high concentration methanol or ethanol 90%-95% can be used for extraction. Whereas flavonoid glycosides, which are more hydrophilic, are often extracted using around 60% methanol or ethanol or hot water. Hot water extraction is economical and safe, suitable for industrial production, and is generally only used for extracting flavonoid glycosides. The alkaline dissolution, followed by acid precipitation, method utilizes the acidity of flavonoids. Acidic flavonoids react with alkalis to form salts that dissolve in water and can then be precipitated upon acidification. When performing this operation, it is important to ensure that the concentration of the alkali is not too high to avoid damaging the flavonoid parent nucleus. During acidification, the acidity should also not be too strong. Otherwise, the precipitated flavonoids may form borates, salts, and dissolve, reducing product yield. If the components contain ortho-dihydratase groups, boric acid should be added for protection. When the medicinal materials are flowers or fruits, lime water extraction is preferred, as it causes water-soluble impurities, such as pectin and mucilage containing carbox or multiple hydroxyl groups, to form calcium salt precipitates, facilitating the purification of flavonoid extracts. For instance, to extract root-in from saforage upon a cabbage, lime water can be used for extraction, followed by acidification with hydrochloric acid to obtain a precipitate. Second, separation techniques of flavonoids. There are various methods for separating flavonoids, mainly utilizing differences in polarity, acidity, and DADS or PTivity for separation. Solvent extraction utilizes differences in polarity for separation. After extracting natural medicines with ethanol, the extract is concentrated to recover the ethanol, and then sequentially extracted with solvents of increasing polarity to achieve preliminary separation. For example, petroleum ether can be used first to remove lipophilic impurities such as chlorophyll and keratin, followed by ether extraction of free flavonoids, and finally ethyl acetate extraction of flavonoid glycosides. pH gradient extraction is mainly used to separate free flavonoids with varying acid strengths. This is the table of flavonoid acid strength and solubility that we learned about in the previous class. How can we use this table to separate flavonoids containing 74 dihydratase, 7 or 4 hydroxy, general phenolic hydroxyl, and 5 hydroxy groups? First, dissolve the total flavonoids in ether. Then sequentially extract with 5% sodium bicarbonate to obtain 7, 4 dihydratase flavonoids, 5% sodium carbonate to obtain 7 or 4 dihydratase flavonoids. 0.2% sodium hydroxide to obtain flavonoids with general phenolic hydroxyl groups. and 4% NaOH to obtain 5-hydroxyflavonoids. Thereby achieving separation. Column chromatography using silica gel, polyamide, and dextran gel are the most commonly used methods for separating flavonoids. Silica gel column chromatography is widely used, primarily for separating free flavonoids with low polarity. Using different proportions of chloroform methanol mixed solvents for elution. Components with higher polarity are eluted later. When separating flavonoid glycan from glycosides, the glycan, which have lower polarity, elute first, followed by the glycosides, which have higher polarity. Polyamide column chromatography relies on hydrogen bonding adsorption for separation. The more phenolic hydroxyl groups there are, the stronger the adsorption and the more difficult the elution. For instance, quercetin and camphor-OL can be separated by pollen chromatography due to their different numbers of phenolic hydroxyl groups. In animation highlights with red flashes the hydrogen bonding between phenolic hydroxyl groups and polyamide, showing the movement sequence of quercetin and camphor-OL for compounds that can form intermolecular or hydrogen bonds. Elution is accelerated. Compounds with more conjugated double bonds elute more slowly. Glycan elute before glycosides. There are two main types of gels used for separating flavonoids. When separating flavonoid glycan, adsorption is the primary mechanism. The more phenolic hydroxy groups there are, the more difficult the elution. When separating flavonoid glycosides, molecular sieving is the main mechanism. Compounds with larger molecular weight elute first. Third, identification techniques of flavonoids. The identification of flavonoid components includes chemical identification and chromatographic identification methods. The hydrochloric acid magnesium powder reaction is an important chemical identification reaction. Take a small amount of the sample, dissolve it in methanol, add magnesium powder and shake. Then add a few drops of concentrated hydrochloric acid. Flavonoids, dihydroflavonoids, flavonols, etc. will exhibit a red to purplish red color. But chalconescent catechins do not show this reaction, and except for a few, isoflavonoids also do not react. Note that if the solution turns red even when only concentrated hydrochloric acid is added without magnesium powder, it indicates that the test solution contains anthocyanins or certain orange chalcone compounds. The sodium borohydride reaction is a specific color reaction for identifying dihydroflavonols, flavonols, producing a red to purplish red substance. Flavonoids can also undergo compoxidation reactions with metal salt reagents such as aluminum salts, strontium salts, and zirconium salts. The aluminum chloride reaction is very commonly used. When aluminum chloride ethanol solution is added to the sample, flavonoid compounds will exhibit a yellow color and bright yellow fluorescence under ultraviolet light. However, for hydroxyflavonols or 7, for dihydroxy flavonols exhibit sky blue fluorescence. The zirconium salts uric acid reaction can be used to identify the presence of 3OH and 5OH groups in the molecular structure of flavonoid compounds. Add 2% zirconium moscow-40-methanol solution of the sample. If a yellow color appears, it indicates the presence of 3OH or 5OH. Then add 2% uric acid methanol solution. If the yellow color does not fade, it indicates the presence of 3OH. If the yellow color fades significantly, it indicates the absence of 3-OH but the presence of 5-OH. Flavonoids can also undergo color reactions with metal salts, such as magnesium salt and ferric chloride, which are used to identify different structures of flavonoids. When a pair of earring-like structures, specific chemical groups are present in the molecular structure of flavonoid compounds. They can react with boric acid under acidic conditions to produce a bright yellow color. For instance, the structure on the left will exhibit a bright yellow color, while the structure on the right will not. Flavonoids with different structures often exhibit different colors when reacting with alkaline reagents. For example, dihydroflavonoids are colorless but can undergo ring opening to form. Chalcones and exhibit color when exposed to alkali. Flavonoids with orthodihydroxy groups are unstable in the presence of alkali and are easily oxidized to form brown precipitates. Flavonoids are often identified using silica gel or polyamide thin layer chromatography. Silica gel thin layer chromatography is better for separating and identifying weakly polar flavonoid Yi-Lei-Con, and an appropriate polarity developing solvent is generally selected. Polyamide thin layer chromatography has a wide range of applications and is suitable for separating and identifying flavonoids and their glycosides containing free phenolic hydroxyl groups, due to the strong adsorption capacity of polyamide for flavonoids. Developing solvents with strong polarity containing alcohol, acid, or water are often used. Paper chromatography is suitable for separating mixtures of flavonoids and their glycosides. For separating flavonoid Yi-Lei-Con, less polar alcoholic developing solvents such as the BW system are generally used. For identifying flavonoid glycosides, more polar aqueous developing solvents such as aqueous solutions containing acetic acid are selected. Classmates, today we have learned about the extraction, separation, and identification techniques of flavonoids, from traditional solvent extraction to modern chromatographic separation. The development of these technologies reflects human ingenuity. I hope you can master these techniques and lay a foundation for exploring the value of more natural drugs. The above is all the content of this class. Thank you all.